Okay, good afternoon, everyone. Okay, so welcome to our tutorial. Okay, so things are moving very fast. Okay, we're already end of week 7. All right, there's another 2 more weeks of studio material to cover, and once we are done with that, basically we are already done with all the actual studios. All right, that means everything that you need to know would have already been taught to you. Okay, so the next step is just to put everything together. Okay, so if you look at what we have been doing in the studios, we have been progressively building up the system, okay, step by step. Okay, and the good part is if you look at the whole structure, the entire framework, okay, which is the the communication between the RPA and Arduino plus the LiDAR interface, the entire framework is actually given to you, correct? So you have just a bit of coding here and there to do, and convert maybe some of the Arduino library code to bare metal code. Okay, that is just some additional work for you to do, but the framework is already given to you. Okay, so if you have been following through on all the studios, okay, you would already be able to have a system that you can remotely control, okay, and navigate. Okay, so uh, it is definitely a very challenging project if you want to code everything from scratch and develop everything from scratch. Okay, so from what we have given you and what we have also seen in all the past batch of students, it is something definitely manageable, all right, for everybody to complete. Okay, so the only thing left is of course the additional sensors that you may need to buy, depending on what is that final challenge that we tell you, all right, what you need to detect and so on. Okay, and of course you would have also noticed in the sample robots that I placed in the lab that some of them also put in IR sensors, ultrasonic sensors, and so on. Okay, those they were put in there by the groups to help prevent any collision with the wall and so on. Okay, so those are of course optional. It all depends on how you want to design your system. Okay, so as we release more details about the uh, challenge that you need to complete, okay, whether it's a color challenge or something else, then you can decide what are the things you need to buy, and you can start working on those additional parts. All right. Okay, so another thing is also the hardware development part. Okay, as I mentioned in the class, if you want to build anything, you want to prototype any uh, sort of boards or things like that, you can always use the makerspace. Currently, the makerspace has some restriction because there's a change of staff handling the makerspace. Okay, so the new staff will take some time to get familiarized with what is happening. So until then, there will be some limited access. Okay, but I believe it should be uh, resolved pretty soon. Okay, and the other thing is of course your driver chips. Okay, so I saw that many of you are of course putting the driver chips onto the breadboard and then connecting the wires and so on. Okay, that is fine, as long as you make sure you secure everything very neatly and nicely. All right, so that is to just prevent anything from accidentally uh, sort of dropping out on the day of the assessment, and then suddenly one motor moves, the other motor doesn't move. Okay, so if you really want to prototype that as well in terms of soldering, you can also do that. Okay, you can ask Uncle Jalil to pass you some boards and some wires, and we can prototype the board as well. Okay, so those are some of the things for you to take note of for the actual project. Okay, so let me move on to the tutorial for today. Okay, so everybody can see the screen. Okay, thank you. Okay, so let's start with the tutorial. Okay, so the first few questions are on the ADC module. All right, so let's have a look at the question. So In the ADC, we saw that we have every time we do A to D conversion, we have a 10-bit result. All right, and in order to update the OCR register, because if you remember the last activity, we wanted to take the ADC value and update the OCR register. So the ADC result is 10 bits, okay, but your OCR register is 8 bits. Okay, and what we can say we normally do is we right shift by 2. Correct? If we right shift by 2, technically it's either we say we divide by 4 or we just discard the last 2 bits. All right, so that is one way of doing it. So if I have the full 10 bits, all right, if I discard the last 2 bits, then I get the 8 bits left. So that is what I think most of you attempted to do, all right, for the studio when we did the last part of copying the ADC value to OCR register. Okay. Now, how could we have directly obtained the 8-bit value without having to do any computation? Okay, that means how is it possible for me to get the direct 8-bit value? Okay, and I don't need to write any code to do it, or don't need to write any additional code to do it. Okay, like what we saw in the studio. Okay, so that comes back to the way the 10 bits are stored in the microcontroller. So since all the registers are 8-bit, okay, to solve 10 bits, we have two registers, correct? We have the ADCH and ADCL. Okay, ADCH and ADCL. And what we saw is the default setting for the result is to hold the 8-bit here and then hold the 2 bits here. So that is the default setting, which is the write justified mode. Okay, so that is actually configurable through this bit file of the AD mux register. Okay, so we did not actually touch this bit in the studio. All right, so the default value is 0, which means it will be write justified. So what is the alternative? The alternative is I can actually do a left justification. So if I were to do left justification, as what you can see in the picture here, the same two registers, okay, ADCH and ADCL, it will be 8 here and 2 here. All right, so if I look at it this way and I want only 8-bit result, so what did I do before? In the past, I got rid of the last 2 bits. So if I want to get rid of this last 2 bits, all I need to do is take the ADCH value, or the value in the ADCH register directly as the 8-bit ADC representation. Okay, so all I need to do is I just choose left justified mode, okay, in my setup of the ADC. So when the result comes, the upper 8 bits will go to ADCH, and I can directly read from ADCH without having to do any other division or shifting or anything like that. All right, so this is something, all right, I'm not sure if any of you tried this during the studio, all right, but this is one way of converting the 8-bit value, sorry, converting the 10-bit value to the 8-bit value directly. Okay, so again, this is an example of the kind of things you can learn, correct, if you look through all the information in the data sheet, okay, when you want to use a particular module. Okay, so of course, in this module, we are guiding you through the process, okay, but in the future, other modules and your project and so on, all right, it's always good to go through in detail what are the things that are already provided for by the hardware. Okay, so if you understand that better, sometimes you can simplify your software a lot, all right, because maybe you already have a hardware module that can do some of this heavy lifting for us. Okay, so in question 2, we are looking at the way in which the A to D conversion is performed. All right, so there are different sort of techniques to perform A to D operation. Okay, so one of the most popular one is, I mean, there are a few different kind of strategies. I think EPP1, we did talk a bit about A to D conversion, but I will not go into those details now. But we will look at how the ADC module in the ATmega works. Okay, so in this, you can see that the A to D conversion, or the A to D converter module already has a DAC also built in. Okay, it has a DAC built in. It is a sample and hold comparator. So if you recall, this is a comparator. It's basically op-amp. All right, that compares two signals, and if V plus, if you remember your op-amp, I hope you do. If V plus is bigger than V minus, the output goes to plus V set. If not, it goes to negative V set or zero. That is your basic comparator operation. Okay, and this is basically the signal that is coming in, the A to D signal, the analog. Okay, and this analog signal that is connected to the plus, okay, and the negative is converted to the output of the 10-bit DAC. Okay, and this conversion logic here, okay, is what we're going to discuss. Okay, so we're going to understand how this whole thing works to give us the correct A to D value. Okay, so that is actually question 2A over here. So what is happening? Okay, when we say start ADC, all right, when we trigger the ADC to start, okay, the sample and hold first gets the signal. So my analog signal comes here. Okay, analog signal comes here, and once I acquire it and hold it at the plus of the op-amp, okay, what will happen is at the very first step, the conversion logic block here will generate a binary code where all the bits are cleared and the most significant bit is set to 1. That means 1, 0, then another 8 zeros. Okay, so that is the first step or the first logic that block will generate. All right, and this will then be sent to the 10-bit DAC. So DAC is the digital to analog converter. All right, and this value here, if you look at it, this is the point where you cross over. Correct? That means when 0, 1, 1, 1, 1 all the way to 1, 0, 0, 0. So that is the point where you cross over. That means it's considered the halfway point of this entire 10-bit sequence. So that is actually equivalent to 2.5 volts. Because the full scale is 5 volts, so the midpoint is 2.5 volts. Alright, so at the output of the 10-bit DAC, okay, in the very first step, you will see a 2.5 volts here. All right, and then what will happen? This sample and hold, all right, will generate an output. Okay, and the output will be based on whether the analog value is greater or smaller than the DAC value. Okay, so if my current analog value is bigger than 2.5 volts, then I will retain this value. That means I keep this value. Okay, if the analog signal value is smaller than 2.5 volts, I clear that bit. That means this one over here will become 0. And then we proceed to the next bit and so on until we reach the end. Okay, so of course, that description is the general one. Let's look at an applied scenario and then we actually see it in action. Okay, so now I'm telling that the input analog voltage is 3.6 volts. Okay, and how will the output be generated based on the operation of the ADC module? Okay, so as what we just discussed, the very first logic that the conversion block will generate is this, where the most significant bit is 1 and the rest are zeros, and that is equivalent to 2.5 volts. All right, so that is the very first logic or the voltage that is generated. All right, and that will give us 2.5 volts at the negative terminal of the op-amp. Now let's do the comparison. So is 3.6 volts greater than 2.5 volts? Yes, correct, it's greater than 2.5 volts. So if it is true, I will keep that bit. So since the most significant bit was set to 1, I will keep that bit. All right, so the current result is what you see here. That means the most significant bit is 1 and all is 0. All right, and then the conversion logic will now move on to the next bit. Okay, so the first bit is now confirmed to be 1. So there's no more change in the first bit. Now we go on to the next bit. All right, so we go to the next bit and we set that bit to 1. All right, so how do I relate these individual bits to actual voltage values? Okay, so as uh, so for the most significant bit, we say is 2.5 volts. Then the next bit, that means the most significant bit minus 1, the next bit is 2.5 divided by 2, which will be 2.5 plus 1.25 is equals to 3.75 volts. Now, how do I get this divided by 2? All right, basically, if you recall, when we say we right shift by 1 bit is equivalent to a divide by 2. All right, so every time I right shift by 1, we know it's a divide by 2. If I left shift by 1, is a multiply by 2. All right, so that is the mathematical sort of understanding, correct? Now, how do we relate that to voltages? So the same thing applies to voltages, all right? Because now I tell you that when the most significant bit is 1 and everything else is 0, then I say that that bit is equivalent to 2.5 volts. All right, so the next bit will be half of that. Okay, 2.5 divided by 2, and then the next bit will be again half of that. All right, so the full 10 bits. Okay, the first bit is 2.5, the next bit will be 1.25, and then 0.625, and then 0.3125 until the end. All right, so every bit, okay, we can apply that divide by 2 principle to the voltage levels. All right, that means if I just activate that one particular bit and everything else is 0, then it is equivalent to a particular voltage as shown here in the boxes. All right, so that is how you relate the voltage to the actual bit position. All right, so now we know that my first bit, just now we saw that the coming back here. So just now what did we do? We already kept the most significant bit as 1, and then we moved on to the next bit and set it as 1. So first bit, most significant bit is 1. The bit next to it is also 1. So the total voltage is now 3.75 volts. Okay, so now that I have 3.75 volts, is 3.6 volts greater than 3.75? So it is no. All right, since 3.65 is smaller than 3.75, that means the bit that I have changed should not be changed. That means I already overshot. Correct? I already overshot the actual analog voltage value that I'm trying to convert. So I switch it back to 0. Okay, I switch it back to 0, and then I move on to the next bit. Okay, so the first 2 bits we have already confirmed that they are 1 and 0. Then I go on to the next bit. Okay, then I do the same thing. So I take 2.5, which is the first bit that is 1, and now this bit 0.625. So it is 3.125, and then I perform the comparison again. Is 3.6 greater than 3.125? Yes. So if it is true, then I keep that bit. That means this bit is supposed to be set. Okay, so the current result will now be 101, and now I move on to the next bit. Okay, so this process will keep on repeating till I finish all the bits. All right, so this is sort of the full table that shows you how to go about, all right, or how the ADC module will go about performing the comparison step by step. Okay, so that is the final result over here that you will get when you try to do A to D conversion, okay, of the module of the 3.6 volts. Okay, so how so of course now we have a better understanding what is happening internally, okay, within the ADC module of the controller. Okay, how can we directly calculate without going through bit by bit is basically what you have been doing in the studio as well. You take 3.6 divided by 5 and then multiply by 1024. Okay, so that will give you a value of 737, which is the same as what we saw just now. So this binary representation is the same as what we saw just now, okay, in the earlier slide. All right, so you can see that if I do the calculation or if I go through step by step, I get the same result. All right, so that now gives us a better understanding of what is happening internally. Okay, now this last question is just to give you some or provoke some thought on what to do in the future. All right, so now we are saying that you want to use an external ADC module for your project. Okay, so what are the important factors to consider before choosing the ADC module? Okay, so the first step or the first thing we'll ask ourselves is, why do I want to use an external ADC module? Okay, so it could be a few reasons. Maybe you want a higher resolution, okay, that your controller does not provide. All right, that could be one possible reason. Another possible reason could be that, as we have seen, all the pins are multiplex, correct? So if the ADC module pins are multiplexed with other pins or other functionality that you need, and you're not able to give up that particular functionality, okay, then you may have no choice but to use an external ADC module. All right, so there could be a few reasons why you may want to use an external module. All right, so what are the factors to consider before choosing the ADC module, okay, an external module? So one of the most important things, okay, would be, of course, the mode of communication. Okay, why is that important? Because now we are saying that you want a 16-bit ADC. That means every time I do a conversion, I have 16 bits of data to collect. All right, so if this 16 bits of this ADC module is going to operate in parallel mode, that means I need to provide 16 data lines just to collect the result. That would be a very impractical solution, all right, because then almost all my pins would be used up, all right, from the Arduino just to connect to this ADC module. All right, so the other options are using the serial interfaces. Okay, so of course we know the UART interface which we have been using. Besides the UART interface, there are other serial interface options, SPI and I2C. Okay, so even though we do not cover these sort of more interface details in this module, all right, they are very popular. So just about many sensors or peripheral devices that you deal with, okay, we'll use either SPI or I2C. Okay, so and of course the good part nowadays is with the abstraction that the Arduino framework gives us, you know, in many cases, even without understanding what SPI is or what I2C is, you can still use these boards and get it working. All right, it's always good to learn. You'll probably learn it in other modules in the future. All right, but it's always good to look out for serial interface modules so that you can connect them up with the least amount of wires. All right, and in many cases you can also share the same wires across multiple devices. Okay, so that is one of the important factors to consider when you want to interface your controller to, for example, a 16-bit ADC module. Of course, other factors are also shown here: power consumption, the form factor, cost, and so on. Okay, so that brings us to the end of the ADC module. Okay, just give me a minute here. Okay, so in part 2, we're going to go to serialization. All right, so the serialization code that we have given you, okay, so you have to be very careful to use the correct code both on RPi and Arduino side in the next few labs or the next few studios, okay, because we'll be extending the serial code further. All right, so one of the common mistakes I have noticed from previous batch students is sometimes they get mixed up in the sense that they use, for example, this week's Arduino code, and then they try to interface with the next week's RPi code, all right, because they think, oh, it's all serialization, so it all should work. No, I don't think that way, because we are extending the serialization code in the next week. All right, so both Arduino side will change, RPi side will also change. All right, so we'll be building upon the current data format structure that we have, all right, to extend it and provide more capability. Okay, so with that in mind, just be very careful that you use the correct set of files for both Arduino and RPi in order to make sure that the correct data format is being used in both sides of the code. Okay. 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 So for serialization, as what we discussed, when you talk about one side, okay, transmitter and receiver, okay, if it's just one data packet, then no problem. Okay, you can just send, you can receive, send and receive and so on. But when you're talking about sending one big chunk of data, all right, that means you have your command, whether you want to move forward, right, left, then how much you want to move, and so on. So that consists of a lot of bytes of information. Now, when you want to send multiple bytes of information over, we usually use a structure. Okay, we use a structure to pack the data with all the different data types that we want to put in. Okay, and if you look at our serialization and deserialization code, okay, what we do is we take everything, okay, and we copy it over into a buffer, okay, an array, okay, and then of course together with that we add in some additional information as well, okay, which is the size of the data, all right, and one more thing is also the checksum. Okay, we'll be looking at that in a while. So over the receiver side, okay, what it will do is it will take this whole serialized data and then unpack. All right, so when over the receiver side, when you receive this same data, okay, it will look at the information, okay, and try to unpack the data into the correct positions in your structure. All right, so of course, as we have seen before and we know, there can always be cases where there is some data corruption, something went wrong and so on. So once your receiver detects that something is wrong, okay, with the data, there is some error detected, then it has to discard the data. All right, it can't process it anymore, it has to discard the data. So in this part of the tutorial, we're going to be discussing on how we can check for errors and how we are able to, or what we can do as a next step. Okay, so the first thing we're going to look at is the checksum. All right, so if you remember in your UART, we have already covered the concept of parity. All right, so the idea of parity is given a certain number of bits, we look at even or odd, and then we append an additional parity bit with the data packet and we send it over. And that parity bit will be used to determine if this byte has any error. Okay, and another thing we've also seen is that it's not a foolproof system. It can detect odd errors, okay, but not even errors. All right, so that is also another challenge that we have to take into account. Now, another layer of sort of checking for any errors is checksum. So how do we derive checksum? Okay, given that we now want to send a chunk of bytes, okay, over the network, over the serial interface. So 0A, okay, we can put everything in binary format here. Okay, so 0001010, that's the first data packet, and the second data packet is 1C. All right, so to derive the checksum, what we will do is we'll perform the Xor operation. So we will first do exclusive OR between the first byte and second byte. So this is the byte 1 and byte 2. All right, and with the result, the XOR result, we will perform another XOR operation with the next byte 3. All right, so XOR with the byte 3 give us a new result, and then XOR with the byte 4. All right, so this is the byte 4. 3A will give us another result. So this is now the final result that we get after we perform all the XOR operations. So this byte here is basically what we call the checksum. Is basically what we call the checksum, which is 6E. Okay, this is 6, this is E. All right, so what we will do is we will be able to transmit this 4-byte data across the network together with the checksum. Okay, so after the receiver receives this data, okay, so when I receive the data, I will receive the 4 byte of data together with the checksum. And what must I do? I must repeat the whole process again, correct, to see the checksum as a match. Okay, if the checksum does not match, then we know that some error has occurred. Then we need to discard the data. Okay, so let's look at this. So this is the data that I send. Okay, and this is the data that I receive. All right, so when I receive the data, okay, so I need to process the actual data part, and then I will check whether the checksum that I get from the receiver side matches the checksum that was sent over to me as well. Okay, so let's look at this received data. So if you look at the received data, I sent 0A, but I received 09. Okay, that means 2 bits are flipped. Okay, originally it was 1 and 0. Yeah, 1010, but now become 1001. Okay, so 2 bits are flipped here. Now, next is 1C. Okay, so 1C received as 1C, there is no error there. Next is 42. 42 received as 01. So this is 0 and so supposed to be 10. Okay, 42 supposed to be 1 and 0 here. Okay, but then it become 01. So 42 become 41. Okay, so I do an exclusive operation here. All right. Sorry, that is the XOR result. This is the 01 here. So this 42 became 41. So this is supposed to be 1 here. Okay, it's red color. So it's supposed to be 10, the last 2 bits. All right, so this is the exclusive OR result. Then I do another exclusive OR with the data 41. All right, and then I get another packet, and then I do one more with the 3A. So 3A is still received as 3A. So that one no issues. Okay, now if I look at the final checksum that I generate, okay, you will see that is also 6E. Correct. So the final checksum that I generate is also 6E, even with the errors. Okay, so what does this tell us? Okay, it tells us that it has a similar weakness where if there is an even number of errors in a column, okay, it cannot detect it. All right, so it is still not a foolproof sort of mechanism to check for all types of errors, but it is still good to have. All right, so that you can detect uh, other types of errors, all right, and hopefully don't do something wrong. Okay, I mean the receiver does not interpret the data wrongly and carry out some unintended action. Okay, so that is basically the part on the checksums. All right, so like I said, the next next week's studios, we will actually be exploring more of these communication protocol, and we will extend upon the current structure that we have, okay, and build upon it. Okay, this last part on LiDAR is basically just a quick recap, just to understand some of the lower level functions that we have been seeing, all right, inside the LiDAR code. Okay, so as we have seen from the LiDAR, all right, how the LiDAR operates is we need to send it, okay, command, all right, from a host. Okay, so you always need a host to talk to the LiDAR first. Okay, so the LiDAR itself is not going to start sending out information. You need to tell the LiDAR what you want, and then it will send some data back. Okay, so many peripherals have some form of communication mode. All right, and this information on how to communicate, what to send, the format of the data, all of this will always be explained within the data sheet. Okay, so that is why we also provided you with the data sheet of the LiDAR. Okay, so if you look at the LiDAR, it is a request response based approach. Okay, and the format they use is the first byte is always a fixed byte of 0xA5. Okay, followed by a 1 byte command. Okay, so this is basically what you always need to send. The rest of it you can see is optional. All right, so when I send a request packet over to the LiDAR, I need to always start with 0xA5, and then I will have to put in a command. Okay, so let me just, before I go on to the next slides, okay, let me just quickly show you where I get this information from. So if you go to your LiDAR datasheet, the LiDAR datasheet has three. Okay, let me share the full screen. Okay, so the LiDAR datasheet has three parts to it. Okay, so one of it is the introduction, where they talk about some general features. All right, so as you can see over here, they talk about the power supply, okay, the digital interface, the communication interface, and so on. Okay, so they're giving you some high level overview of how things work. All right, so that is the some of the electrical characteristics, performance, and so on. Okay, communication wise, they also tell you what are the pins and okay, how the connector actually works. Okay, next is the other data sheet, which is the interface protocol. So this is the important document, because this will determine how we write the firmware. Okay, so for us, luckily we have the entire library given to us from the manufacturer. Okay, so in most cases, the manufacturers will definitely provide the libraries and APIs that you need to use to communicate with their device. All right, that's the way. That's the only way they can sell the product. All right, they can't sell you a hardware and say you have to write your own software. Then nobody will buy. All right, so generally most peripherals, okay, when the manufacturer gives you, they will also have to provide you with some software interface to make it that can allow you to quickly get started using with it. Okay. Okay, so if you look at this, okay, so they again give you the TX, RX, the ground, and so on. Okay, and they tell you about the request response format. All right, so inside here you can see all this information, and this is from where you can extract all the necessary data on how it works. All right, so that is the main document, and whatever I'm showing here is actually extracted from the document. Okay, so in terms of communication mode, all right, when you send a command, all right, that means when I want the LiDAR to do something, I must send it a request. All right, and when I send a request, that request will have a start flag, which is the A5, followed by the command. The command is what do I want it to do for me. Okay, then when the LiDAR responds back, okay, you will have two types. One is the response descriptor, and the other one is the data response. Okay, response descriptor, okay, will be giving us some information on what kind of response you're going to expect. Then in cases where I expect a lot of data coming back, like when he's doing a scan, all right, then it will also tell you how many data packets are going to come through with the scan information. All right. Now, in terms of response descriptors, this is how it looks like. So the first two bytes are A5 and 5A, all right, followed by the data response leg. That means this is telling me the length. So I use 30 bits to tell the host how big is my data. Okay, how big is my data? All right, followed by the send mode. Okay, whether I will send only one response or multiple response. Okay, so either this or this. Okay, so in a case where I just have to send back maybe uh, a bunch of data that can fit in uh, within one response packet, then you can say it's a single response mode. But in maybe a scan mode, you have a lot of data continuously coming through, so you will have a multiple response mode. That means you keep on receiving a huge chunk of response data packets. Okay, so in terms of response, all right, again, you can have a single type of send and reply. So I ask you something and you reply me back something. In some cases, is this response will have a lot of data. Okay, that means you have a response descriptor as well as data response. All right, and in other cases, you may have multiple data response. All right, so it all depends on what kind of mode operated. Request response is one way, the other one is request with multiple response mode. All right, so this is very much like how your scan is being done. All right, when you do a LiDAR scan. Or in other cases, it could also be what you call a no response mode. That means you send a request just for it to do some operations, all right, and then there is no response. Okay, so for example, maybe there is a command to stop the motor. It might not respond to you that the motor has stopped, all right, it will just carry on the action. Okay, and then you have to issue the next command after that. Okay, so it could also be this kind of communication mode. All right, in terms of the code, all right, you can refer back to your files, all right, that were given to you. So there are a few files, the rp lidar driver.cpp file. Okay, so if you look at your code base, okay, so let me just come back to the code here. Okay, so of course you're not expected to understand all this library code here, but roughly if you look at what is happening, okay, you can have an idea of the kind of operations that are going on. So if you look at it in the main, all right, the very first thing we try to do is, of course, we get the device info. Okay, we connect. Okay, so of course we try to connect, make sure that we can establish connection based on the baud rate and the path that we set for the LiDAR and so on. And then we try to get the device info. So the device info will tell us the serial number, okay, of the device. Then from there we can print out what is the firmware version, hardware version, and so on. All right. And why is this kind of information important? All right, because in some cases you may have some upgrades, all right, that the manufacturer has provided, and you may want to check whether your firmware version is up to date. Okay, and you may want to refresh it with the updated firmware. All right, then the next thing, as you can see here, we try to get health info, and then from the health info we check whether everything is okay. All right, so only if it is okay you will be able to carry on. All right, and then once it is okay, we can say start motor. All right, and once we start the motor already, we start the scan. All right, and if the start scan is successful, you will do a capture and display. All right, so you can see the sequence quite clearly what is happening. All right, even though the code is not something that we expect you to understand, but if you look through the sequence, you can roughly get an idea the whole operations of what is happening, okay, when we try to use this LiDAR. Okay, so the get device info, all right, if you look further into the code, you will see that I send 0xA5 sync byte followed by 0x50. All right, so that is the command I send over to the LiDAR. Now, how do I know it's 0x50? So this 0xA5 is a sync byte. That means the first byte that we send, the host sends to the LiDAR has to be 0xA5. All right, then the next byte is telling it to do something, the command. All right, so that is inside the header file or inside your datasheet as well. So you can see down here that the request that I want is tied to a particular code. So in this case, if I want to get info, then I say 0x50. When I want to do a scan, it will be 0x20. When I want to get the help, it will be 0x52. So depending on what is the command I send over to the LiDAR, then the LiDAR will carry out the necessary action. Okay, so after it carries out the necessary action, it will send me back some data. All right, we have to send me back some data. In this case, it will be, the response will be 0xA5 and 0x5A. So the response, if you look at it, is always starting with A5 and 5A. Okay, and in this case, we are putting in a value of 14000000, and this 14 is telling me that the number of bytes for the device info. Okay, the number of bytes for the device info that would be sent. All right, and after I send the initial response which is this. So this is the first packet that will come back. All right. After this first packet comes back, okay, then another 20 bytes will come back. Okay, and this 20 bytes will consist of this information here. Okay, so you can see that the data, all right, will come back based on the way the firmware has been developed for the system. All right. So again, if right now you look at it for the first time, okay, then it may be a bit uh, confusing. But if you look back at the data sheet and you look back at the code, you can sort of relate it together. All right. Now, if I want to get the health information, again the same thing, A5 and 52. Why 52? Because just now the command said that get health is 52 over here. So after that, what happens? You will receive a response, okay, which is A558, and then telling us how many bytes, all right, for the health info. All right, so you expect 3 bytes for the health info. All right, so again, how many bytes you have for different types of info is given in the data sheet. Okay, it's not something that we figure out by ourselves. We look at data sheet, we look at the code, and then we can understand what is happening. All right, so again, this tutorial here is just to give you, or this part here just to give you the idea of how the LiDAR communicates, okay, and how things work between the host and the LiDAR. All right, and I think what we want to just show you is that, all right, this information that we get from the data sheet, okay, we need to relate it closely with the firmware to understand what is happening. All right, so of course in this project we are not going to mess around with how the LiDAR behaves, okay, or how it works, but maybe in the future if you want to do other things, all right, that with the LiDAR on your own, you may want to look at this kind of code base more closely, so to understand exactly where is the data coming through, how else I can change the behavior of the LiDAR or things like that. All right, so the firmware that is provided, you can sort of modify on your own to change the behavior if you want. All right, so that is what the objective is. Okay, so that brings us to the end of the tutorial. Okay, so it's a fairly short tutorial. Okay, so before we end, maybe let me just quickly check the lesson plan again. Okay, just so we can understand where we are. Yeah, so next week, okay, the first one is to go remote. Okay, that means we are going to uh, communicate through the cloud. All right, and then we're going to have another studio on secure communications. All right, and then finally we'll be on the SLAM and then power management. Okay, so just a few more studios. All right, and then the rest of the weeks is for you to do your own work. All right, and build up the robot. All right, and I think next Friday you also have a CLC workshop. So you won't have tutorial, you have a CLC workshop. Yep. Okay, so anyway, we will discuss more on that in the next studio on Tuesday. All right, so next Tuesday studio, I believe is graded. Yeah, so Alex goes remote is graded. So please check through that material, all right, before coming to the lab. All right, so you know exactly what to do. Okay, so does anybody have any questions so far on the project uh, and things that are happening in the lab so far? Anything you want to ask? All right, so for the purchase of components, please, if you look at the documentation given by Colin, it is stated clearly you have to buy locally from local stores. Okay, so you are not allowed to buy anything from online. Okay, so and you have to make sure you keep your receipt so that we can process the claim for you. All right. Again, from feedback from past batch of students, the claim is a very long and slow process. Okay, so do not expect that you will be reimbursed very quickly. It will take quite a while. Okay, so just be prepared for that part alone. Okay, but other than that, I think the rest of it should be fine. Okay, so does anybody have any questions you want to ask? Anything you want to clarify about the project or about anything going on in the lab so far? Okay, so if no questions, I think that's all we have for today. All right, so next week, again, just remember that next Tuesday's lab is graded. So please come prepared, and then I will see you all in the studio. Okay, so thank you very much. Enjoy your weekend. Okay, I'll see you all on Tuesday.